Okay, so now we are going to learn the methodology of variation of parameters method. Now this is little bit identical to what we did in integrating factor method in section 2.3 and then also for the reduction of order method. Okay, all right. So the first thing that I would like to have is the standard form. So let's write our differential equation in the standard form. Okay, so that means the coefficient of y double prime should be 1. Okay, now once you do that, the first step is to solve the homogeneous version of the differential equation. So we solve this equation right here. Okay, you can use, if you have constant coefficients, you can use auxiliary equation method, or sometimes the solutions for the homogeneous differential equation could be given in the problem itself. So read the problem very carefully. Okay, all right. So since this is a second order differential equation, how many solutions you can find for this homogeneous one? 2, right? And what do we call them? Fundamental set of solutions for the homogeneous equation, or the complementary solution, right? Okay, good. Now you know y1 and y2. Either you find it by yourself, either it will be given in the problem, okay, to make your life easy. Okay, then the next goal is, well, we know the complementary solution. Let's find out what is the particular solution. So we assume yp. This is the big assumption in variation of parameters. It's look like u1 times y1 plus u2 times y2. Now here, this is a trial form again. This is quite a bit similar to what we did in method of undetermined coefficients. You assume your particular solution is going to look like this and that, and then you resubstitute it back to the differential equation so that you can figure out the correct form of the particular solution, right? So this is sort of like a trial form. So in method of undetermined coefficients, remember you had a, b, c, d and so on constants. But in variation of parameters method, the difference is you will have unknown functions u1 and u2. They are functions. So our target is to find out u1 and u2. Okay, all right. Okay, so now we are going to substitute yp back into the differential equation. So this is where I'm just going to explain steps. I'm not going to show you work because it's extremely tedious to, okay, show that in a small video. Okay, now to substitute, of course, we need to find y prime and y double prime, and you have to use product rule here because u1 is a function, y1 is a function, u2 is a function, y2 is a function. So you have to apply product rule several times. Let's say you get y prime and y double prime like this. Now when you substitute it back to here, well, this is what we get, a rather a long expression. Okay, now again, this is similar to what we did in section 2.3 and also in reduction of order method. Now what we're going to do is we're going to regroup what we substitute in. Okay, so I'm not going to show you all work. So this is what I get after I regroup. You can already see it's pretty long. Now focus on the red color parts, what I have highlighted on the red color here. Okay, those are very similar to our differential equation, right? But instead of y, we have y1 here, okay, but it is similar to what we have here. Now y1 and y2 is the solution for homogeneous differential equation. So how I can read this part is I have substitute y1 into the differential equation. Now what do you get if you substitute y1 to the differential equation, or y2? You should get 0, right? Because that is exactly what it means. y1 and y2 are the solutions for the homogeneous differential equation, meaning you get 0, not f, right? So here these terms will become 0. So that helps, right? Okay, that's sort of a shorter, our longer expression, right? Okay, let's try to erase several stuff. Okay, so these two terms will vanish. Okay, so let's do not look at them. Okay, so we shrink our left hand side. Now what we can do is we again try to regroup. Okay, so if you look at these four terms here, we can rewrite them as, you can think them as the product rule of these two. So if you differentiate y1 and u1 prime with respect to x, you have to use product rule. Okay, this is exactly what you get if you use the product rule. So y1 u1 prime, if you differentiate this, what you get is y1 prime u1 prime. Okay, apply product rule. So you just differentiate y1 and keep u1 prime unchanged. Now keep y1 unchanged, differentiate u1 prime, then you get u1 double prime. This is exactly what you have in the first term, right? That's right. This is reversed, but order doesn't matter. And this is exactly what you get after you apply the product rule here. So looking at those two terms, we were able to think back product rule reverse. Okay, so then we can rewrite what you have in this longer expression like what you have here. Okay, all right. Now don't get worried or don't get amazed how I'm supposed to do that when I get a real examples. You're not going to deal in that. Okay, so we are going into the easier part. Okay, so be with me. All right, so again I can combine these two and rewrite these first two terms as a one term, and I get this. Okay, so now I get a much smaller left hand side. Okay, so now you can see I have highlighted something from dark blue color. So what we are going to do is we are going to make another assumption. The assumption is that we are going to assume this dark color term, blue color term, is to be 0. Now that is a condition. Now, why do we impose the condition? So the reason is we want specific u1 and u2 such that they obey this condition. Okay, again this condition make our life easy, because if this is 0, these two terms are 0, right? Boom, those two are gone. Okay, all right, so what's left is then this part here is equal to fx. So that is exactly what I have written here. So we impose this condition and the first two terms vanish because they are 0, and we get two conditions. Okay, so meaningly two equations, two simultaneous equations, you can see. Okay, so that is the final goal of, that is what we get after doing those regrouping and logical analyzing and imposing conditions. Okay, now when you come to here, well, we can solve this using Kramer's rule. Now let's try to write this simultaneous equation as a matrix equation. That means I can rewrite this left hand side as y1 y2 y1 prime y2 prime. Okay, extracting the coefficients of u1 prime and u2 prime. Here the vector u1 prime u2 prime, and if you multiply these two, this is exactly what you get. Okay, this is equal to 0 fx. If you have taken linear algebra, you know what it is, what this is. Okay, you should have taken linear algebra before this course anyway. So that is how you can write a simultaneous two equations in a matrix form. Now to solve this system, we can use the Kramer's rule. Okay, now if you look at this coefficient matrix here, y1 y2 y1 prime y2 prime, can you remember something it from section 4.1? That's the Wronskian, right? Remember? That's the definition of Wronskian for two functions y1 and y2. So this system is like, you have to solve this for u1 prime and u2 prime. So that is what we are going to do. So to do that, we use the Kramer's rule. Okay, so let's assume w is the determinant or the Wronskian of this coefficient matrix on the left hand side. Okay, so by Kramer's rule, we can find u1 prime, what you have here, by the formula w1 over w. Now w1 is actually, by the Kramer's rule, if you want to find the first variable, you replace the first column by 0 fx, the right hand side vector, and you keep the second column unchanged. So y2 prime, divide by the determinant of the original coefficient matrix, which is the Wronskian, right? Wronskian is the determinant. So you get u1 prime. And then similarly, you can get u2 prime by replacing the second column by 0 and fx. Okay, so u1 prime can be found as w1 over w, w2 over w. Now w2 is, again I'm saying, you replace the second column in the coefficient matrix by 0 and fx. That's just the Cramer's rule. But if you simplify this w1 over w1, so w1 is actually 0f y2 prime. So actually the determinant here is y2 prime times 0 is 0. So 0 minus y2 times f is y2f, negative y2f. So w1 is actually negative y2f. So that is how I get negative y2f here. So u1 prime is actually negative y2f over w. Okay, w is a function, that is a determinant. You will get a nice one function. Okay, it's not a matrix. So similarly, you can find u2 prime as y1 times f over w. Okay, all right. So now we know u1 prime, u2 prime. Okay, so let's write it down. Let me show you. So u1 prime is negative y2 times f over w, u2 prime is y1 f over w. Now how can you find u1 and u2? Because you are not looking for u1 prime and u2 prime. How can we find u1 prime, u1 out of u1 prime? Well, you integrate, right? You take the antiderivative with respect to x. So then if you integrate these two, you get u1 and u2. So we get nice formula set just like here. Okay, and then you know u1 and u2 because you know y2. Think about this. If you want to find u1, you know y2, right? You know f. F is the right hand side of the standard form of the differential equation. W you can find because you know y1 and y2. Then u2, similarly you can find u2. Then using these two formulas you can find u1 and u2. Then you can find the particular solution because u1 times y1 plus u2 times y2 is the particular solution. Then the general solution is complementary function time plus the particular solution. Okay, so I know it's sometimes this may sounds like a very complicated and you might think that you are lost, but let's summarize and understand the steps, and when I do an example it will make sense. Okay, so what are the steps? Let's clear our head. First step is write the differential equation in standard form. Okay, then solve the associate homogeneous differential equation for y1 and y2. Okay, so you might use auxiliary equation method, or sometimes y1 and y2 will be given in the question. Okay, so read carefully, then you can reduce the workload. So find y1 and y2, then find the Wronskian. Now see, you are not going to do the lot of work that I have explained here. Okay, so you're not going to do that when you're solving an actual example. It's just we found a method. Okay, that's it. So you can find the w because you know y1 and y2. Okay, so you can find the Wronskian, that's a determinant, that will be a function. Okay, now we use the formulas given here, u1 and u2 given here, to find u1 and u2 because you already know y2, you know f, you know w. So you just do a simplification inside the integral and you do an integration twice here and here. Then you can find u1 and u2. Then you can find the particular solution as the u1 that you found times y1 plus u2 that you found times y2. Then that is your particular solution, and you write the general solution finally as yc, complementary solution that you find plus particular solution that you found. Okay, so that's a methodology. Try to see how I do examples and I hope it will make sense. Okay, all right, thank you.